performance play an important role in ensuring smooth factoring operation and consistent production output. One key factor that affects the performance is operating time of machine per day, while production output refers to the amount of good produced within that time. In real factory setting, machine may experience issues such as inconsistent operating time, minor faults, overheating or maintenance delay, which can reduce their productivity. Therefore, it is important to understand the relationship between the machine operating time and daily production output to better understand on how much machine usage can affect the efficiency and overall performance. Objective of study. The objective of the study are threefold. First, to identify the relationship between machine operating time and daily production output. Second, to develop a linear regression model based on the data. Third, to use a regression model to predict daily production output. Next, moving on the significance of study. This study is significant because it has factored manager and operator make a better decision regarding the machine usage. By understanding how operating time can affect the output, the factory can improve scheduling, reduce downtime, and also increase the productivity. In addition, this study also contributes to the knowledge of statistical analysis by showing how correlation and regression can be applied in real industrial situations. Moving on the limitation of study, despite its benefit, this study has several limitations. It only focuses on two variables, which is machine operating time and production output. Other factors such as machine condition, worker skills, maintenance schedule, and raw materials availability are not included. This study also depends on the accuracy of second data, which may affect the result. Therefore, the finding may not fully represent all real-world production conditions.
Next, I want to present about the methodology. Firstly, data equation. The study analyzed the relationship between operating time per day, measured in minutes, and production output measured in kilogram per day. The datasheet consists of 10 production machines, labeled from machine 1 to machine 10. The data were obtained from SPSS version 3 output, making it secondary datasheet. The location of the study was not specified. The objective of this study is to determine whether the longer operation time is associated with higher production output and evaluates with overall performance trends of the machines. Both variables used in this study are quantitative continuous variable and are measured on a ratio scale as they are numerical, continuous, and have a true zero value. Next, let's move on to the graphical technique. Graphical technique were used to visually examine the relationship and distribution of the data. Firstly, the scatter plot was used with operating time on x-axis and the production output on the y-axis to identify any linear relationship, clustering patterns, or outline. Next, a box plot were used to summarize the data distribution by showing the minimum, quartiles, median, and maximum value as well as to detect potential outlier. Lastly, a histogram were used to assess the distribution of operating time and the production outputs, including spinous and normality. Finally, I will explain about numerical technique. Numerical technique were used to summarize the data and to analyze the relationship between operating time and the production output. Firstly, measure of central tendency. Measure of central tendency were used to describe the central value of the data, which include the mean, median, and the mode for grouping. The mean represents the average of the data values. The steps involved are finding the class midpoint, calculating fs, and dividing the total fs by the total frequency. Next, median. The median is the middle value of the data when arranged in ascending order. The step include contrasting a cumulative frequency table, finding the median position, and divide by 2, identify the median class, and applying the formula. Lastly, mode. The mode is the value that occurs most frequently in the datasheet. The model class is first identified, and then the mode is calculated using the formula or estimate from the histogram. Let's move on to the assumption. For mean, the mean assume numerical data with an approximately symmetry distribution, and then the median is suitable for ordinal or numerical data and is not affected by extreme value. Lastly, the mode can be used for all types of data and is especially used for categorical. Next, correlation analysis. Correlation analysis was carried out using creation, production, performance correlation coefficient to measure the strength and the direction of the relationship between operating time and production output. The value of R lies between -1 and +1 when we look at the formula. Next, coefficient of determinations. The coefficient of determinations are power of 2 represent the proportion of variation in the production output explained by operating time R times R. Lastly, mode. The mode is the value that occur most frequently in the datasheet. The model class is first identified and then the mode is calculated using the formula or estimate from the histogram. Let's move on to the assumption. For mean, the mean assumes numerical data with an approximately symmetry distribution, and then the median is suitable for ordinal or numerical data and is not affected by the extreme value. Lastly, the mode can be used for all types of data and is especially used for category data.
For this study, we collected data on operating time per day in minutes and production output in kilograms per day from 10 randomly selected observations. The data is used to examine the relationship between operating time and production output. This scatter plot shows a positive relationship between operating time and production output. Each point on the graph represents one observation from our data. As operating time increased, production output also increased, and the point from a strong linear pattern indicating a very strong positive correlation. First, we analyze the operating time data. The total operating time is 5,370 minutes, and with 10 observations, the mean operating time is 537 minutes. After arranging the data in ascending order, the median is calculated by averaging the 5th and 6th values, which give a median of 543 minutes. This means that 50% of the observations have an operating time of 543 minutes or less, while the remaining 50% are above 543 minutes. The mode shows the most frequent operating time among 10 randomly selected is 360.67 minutes. Next, we analyze the production output. The total production output is 5,094.9 kg per day, giving a mean production output of 509.49 kg per day. The median production output is 517.95 kg per day, which is obtained by averaging the 5th and 6th value after sorting the data. This indicates that half of the observation produced 517.95 kg per day or less, while the other half produced more than this value. The mode shows the most frequent production output among 10 randomly selected is 442 kg per day. Correlation coefficient R equals to 0.999 indicates a very strong positive correlation between operating time and production output. This means that as operating time increases, production output also increases. The result is statistically significant with a p-value of 0.001, showing that the relationship is unlikely to occur by chance. The R-squared value is 0.998, meaning that 99.8% of the variation in production output can be explained by operating time. The remaining 0.2% of the variation may be due to other factors not included in this model. Referring to the unknown table, the I value is 4,754.643 with a p-value less than 0.05. This result shows that the regression model is statistically significant, which means operating time has a significant effect on production output. Therefore, we can conclude that the regression model is fit and reliable for explaining the relationship between operating time and production output. This slide shows the coefficient of the regression model, which explains how operating time affects production output. The regression equation obtained is y equals to 39.527 plus 0.875x, where x represents operating time in minutes and y represents production output in kilogram per day. The constant value 39.527 indicates the estimate production output when operating time is 0. The slope coefficient b equals to 0.875 means that for every 1 minute increase in operating time, production output is expected to increase by 0.875 kg per day. The p-value is less than 0.001, which shows that operating time is statistically significant predictor of production output. Therefore, operating time has a significant and positive effect on production output.
Last but not least, let's move on to the conclusion. First, a strong positive relationship. The analysis shows that emission operating time increases. Production output also increases significantly, indicating a direct and strong relationship between these two variables. Second, the high correlation coefficient and linear regression models. This value is very close to 1, which confirms that longer mission run times are almost perfectly associated with higher production output, and this model shows that operating time can be used to predict daily production output accurately. Next is interpretations of regression, which is each additional minute increases output by approximately 0.875 kg. This means that even small increases in operating time can be linked to measurable improvements in production's output. Now let's talk about what are the future recommendations. First, future studies should include additional influencing factors. For example, production output is not only affected by operating time but also by factors such as machine condition, operator skill, and material quality. In addition, apply multiple regression models. Including more variables in the model will allow for more accurate predictions and a deeper understanding of how different factors interact. Next, collect data over a longer time period. This helps reduce short-term fluctuations and improve the reliability of findings. Use advanced methods such as time series analysis, and this method can identify production trends and mission behavior patterns over time.